W. Next problem. For this given particular beam, cantilever beam, subjected to the UDL 10 kilonewton per meter, the length of the beam is of 2 meter. Only one load is acting, that is of UDL. Now, as we discussed the previous case, if we take from the right case, then there is no need to find out the support reaction. It is utmost necessary to learn over here that for a cantilever beam, if we want to find out the variation of shear force along the length of the beam as well as the variation of bending moment along the length of the beam, it is not necessary to find out the support reaction at the prior stage, at the first stage, if we will take the section from the right side. But even though it is our practice to find out the support reaction, hence let us find out the support reaction first. By using the equilibrium conditions, if we take sigma h is equal to 0, none of the force which is acting externally over here is horizontal, means RAH is equal to 0. If we will take sigma V is equal to 0, then here RAV is acting at this case assuming upward. So total upward force is equal to total downward force. Therefore, RAV is equal to total downward force is equal to 10 into 2, 20 kilonewton. As if over here fixed end is acting, fixed support is acting, the third reaction is of moment over here. We are assuming it is as if anti-clockwise direction. So by taking moment at A, the first is minus MA plus the moment due to this UDL plus Y, because it creates a clockwise moment. So 10 into 2, it is the total load, into 2 by 2, that is the distance from the CG of load to the point of application A, means minus MA plus 10 into 2 into 2 by 2, and we will achieve MA is equal to 20 kilonewton into meter. The positive sign indicated that our assumed direction of MA is of anti-clockwise at A is right. Now let us plot the shear force diagram and bending moment diagram using the tabletop. Given beam is of cantilever beam. UDL, the beam length is of 2 meter. Baseline. Now let us take a section over here. Distance x from B, shear force at XX is equal to unbalanced vertical force either from the left or right of the section. Here from the right of the section, unbalanced vertical force, that is of 10 into x. Here section force acting right downward, treated as positive. See, this is the equation, linear straight line equation. So if we put x is equal to 0, SF at B is equal to 0. But if we put x is equal to 2 meter, SF at A is equal to 10 into 2, that is equal to 20 kilonewton, that is the reaction at A. So these two ordinates are known to us, 20 and 0. Linear equation, we will join this with the help of inclined straight line plus sign. This is my shear force diagram. If you want to take the distance 0.5 meter, find out the value of shear force. Take a 1 meter, find out the value of shear force. Take a 1.5 meter, find out the value of shear force. By putting the value of x as 0.5 meter, 1 meter, 1.5 meter, you can also achieve the various ordinates. Join these ordinates and we will achieve the inclined straight line. Now let us we go for bending moment diagram. This is our baseline. Positive values above the baseline, negative values below baseline. Refer this particular section from the right side. Then bending moment at x-axis is equal to 10 into x by 2, because this is the load. Load multiplied by perpendicular distance, that is CG of load to the reference axis x by 2, and this is equal to 5x square. Variation of parabolic nature. That is very much interesting point. Variation is of parabolic nature. Now, whether this parabola is which one? Can I adopt it this one, or can I adopt it the hyperparabola? Which one I will adopt? Let us see by taking the intermediate point results. So first one, take x is equal to 0, my bending moment at B is equal to 0, because when x is equal to 0, just visualize over here, my bending moment variation we can achieve at B. Now x is equal to 1 meter, bending moment at center is equal to 5 into 1 square is equal to 5 kilonewton into meter, and when x is equal to 2, I will achieve bending moment at A is equal to 5 into 2 square is equal to 20 kilonewton into meter. Just visualize, if this is my baseline at B point, this is my A section, it is 0 over here, this is the value 20 over here, and the intermediate point is of 5. I have to join these points. So if you want to go more precisely, you can find out at 0.5 meter what is the ordinate, you can find out at 1.5 meter what is the ordinate, and you can join those ordinates and we will achieve parabola. Now sign convention is very much important. Section right clockwise. So if we take a section right clockwise, which is treated as negative, so all the values we achieve over here is of negative below the baseline, minus sign, and this is my bending moment diagram. So from this we follow the rule, the same rule that we used in case of simply supported beam. Beam with parabola, beam with UDL, the variation of bending moment diagram is given by parabola, and bending moment diagram, shear force diagram, which is shown by inclined straight line. The same rule is applicable for a cantilever beam. So the same case you can visualize over here at this PPT. So the variation of shear force diagram, which is given by inclined straight line, while the bending moment diagram variation is given by parabola. So I think now you can plot the shear force and bending moment diagram for point load as well as for UDL. Now let us we take a third particular beam, same beam, cantilever beam, but the load which is applied with some bracket connection over here. Means the load is applied at horizontal distance is of 0.3 meter from this B, and vertical this distance is of 0.2 meter. This particular beam which is given to us. So our first step is simplify the beam and apply this point load on this beam itself instead of providing the load on the bracket connection. Let us apply this load on this beam itself. So my simplified figure is over here. This 20 kN load shifted over here, which generates anti-clockwise moment 20 multiplied by this distance, that is of 0.3, 20 into 0.3, that is 6 kilonewton into meter, that is the anti-clockwise moment. So this point load shifted at B with the point load as well as the moment at B. See this particular figure. Point load is of 20 and the moment is of 6, which is applied over here at B. Step number 1, as usual, find out the support reaction. Sigma H is equal to 0. No horizontal force acting in the system. RAH is equal to 0. Sigma V is equal to 0. Then in that case, the two forces, first reaction as well as this 20 kilonewton load, is acting only along the system. So RAV/VHU 20 kilonewton. There is no contribution of this 6 kilonewton into meter to find out this RAV, because it is a moment is acting over here at this P, concentrated moment. Sigma MA is equal to 0. That is application of all the moment of the forces at this point. So assuming sign convention is of anti-clockwise over here for MA, so treat it as negative minus MA plus 20 into distance, that is of 1.2. Now this concentrated moment is acting over here, which is sign is of anti-clockwise, so minus 6 is equal to 0. So by simplifying this, VHU MA is equal to 18 kilonewton into meter. This positive sign signifies that our assumed direction of MA is of anti-clockwise is of right. So MA is of anti-clockwise nature, the value is of 18 kilonewton into meter. Our intention next is to plotting of shear force diagram and bending moment diagram. It is we understood in this tabletop. Cantilever beam with point load, moment 6 kilonewton into meter at B. Distance is of 1.2 meter. Now in this particular problem, instead of taking a section, let us we directly draw the shear force diagram by applying the basic concept. If we take a section over here, only one force is acting, unbalanced force on the right side, that is of 20. So section right downward 20 treated as positive 20. No contribution of this 6 on the shear force diagram. No load is applied other throughout the length of the beam. Variation is of horizontal straight line, and the reaction, it is known to us, 20 kilonewton, it is of 20. Sudden changes there, plus sign. This is my shear force diagram. Now let us go for the bending moment diagram. This is my baseline. if we take a section over here, section XX, moment and load both are acting. So bending moment at XX is equal to section right anticlockwise. So see the sign convention, section right anticlockwise. This is nothing but our positive sign convention, that is, this is the sagging moment. So plus 6. This creates section right clockwise, minus 20 into x. See this equation at section XX. Now if we go for x is equal to 0, that is bending moment at B is equal to plus 6, because 20 into 0 it is 0. So the unbalanced moment is of plus 6 at B. So if we plot, this value is of plus 6 value. Now if we go for x is equal to 1.2 directly over here at A, bending moment at A is equal to 6 minus 20 into 1.2, that is equal to minus 18. As this is nothing but the bending moment that we found out over here in the steps of reaction. So this is 18 with minus sign. I have to join this and see this equation, linear application, inclined straight line. This is nothing but inclined straight line. This is negative, this is positive. You can verify this diagram by taking the intermediate section of 0.3 meter, 0.6 meter, 0.9 meter, find out these ordinates and then join these ordinates, and we can obtain the same diagram. The same